Hey, I'm Neel, and I run the Google DeepMind mechanistic interpretability team. I'm here to chat a bit about our work and how this fits into the broader picture of alignment. This is just one part of our broader alignment portfolio. I generally see interpretability as being about enabling all of the other work we're doing to try to make these systems safer. So, what is mechanistic interpretability? A common belief is that machine learning systems are just inscrutable piles of linear algebra. They're more grown than designed. We don't tell them how to do the rich, complex tasks they're capable of. We just give them vast amounts of data, and they seemingly learn how to do this entirely on their own in ways that need not make sense to us. But I believe that mechanistic understanding of neural networks is possible, that they do learn rich underlying structure, and that we can understand this if we know what we're doing and we know how to reverse engineer it. This is a pretty bold claim. Why do I think this is possible? I think one of my main sources of optimism is just the level of success that past interpretability work has had finding rigorous insights in complicated models, starting with early work like this paper from Nick Camerata on curve detecting neurons. They took a convolutional neural network that was trained to identify which category different images were classified into, and they found that it had spontaneously learned neurons that could detect curves in images, from neurons that detect simple curves earlier on to more complex neurons that piece together all these simple curves into larger curve detectors, as shown in the diagram here. They were able to understand the algorithm behind this to such a level of detail that they were able to write down a computer program to generate the weights of this network, to generate artificial versions of these neurons, and were able to substitute these in for the curve-detecting neurons, while still preserving part of the model's performance. And there's been a lot of progress in the field since then, most notably the technique of sparse autoencoders, which essentially let us see what a language model is thinking about. Here's a picture of a sycophancy feature that Anthropic found in Claude Sonnet 3. This activates on text to do with effusive, over-the-top praise. And we can not only see when the model is thinking about or using this concept, but we found something that's causally meaningful. We can set it to an artificially high value on text that isn't about sycophancy, and now when the model says things, it just seems to inject lots of effusive, praise-focused content. So, why does any of this matter for alignment? At a very high level, I think this matters for alignment, because if you understand what a complex black box system is doing and what it is likely to do, you are likely to be better able to control it and to understand it significantly better than the status quo, where these are kind of mysterious black boxes. And this seems like a pretty big deal in general, but trying to unpack this and dive into more specifically what's going on, I think there's maybe two separate worlds that are worth distinguishing. Worlds where we have some runaway success with interpretability, and can do hard, ambitious tasks directly, like dealing with deceptive alignment in models, and worlds where we have more moderate success. We don't necessarily get that far, but we can still learn meaningful things about these systems with interpretability. In the ambitious success worlds, we can do things like reliably audit a model for deceptive intent. We could potentially even enumerate everything a model can do, and look for unsafe behaviors. With more moderate successes, we could still ideally do things like taking weird and unexpected behavior and trying to reverse engineer it and debug why it happened and how it could be fixed, or monitoring a system's behavior when it's deployed, and looking for anything problematic or unusual, or trying to red team a system, that is, trying to trick it into doing dangerous or unexpected things, and seeing how much it's capable of. I expect more and more uses will come up as we just better explore problems with these systems and ways we can make them safer. So yeah, thanks for learning about interpretability and some of my team's work with me.